Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Very happy for the final speaker of today, Roberto Oliveira from IMPA Brazil, who will tell us on bounding the time for mixing of symmetric exclusion in terms of one particle mixing time.
Well, I'd like to thank you all for being here, those who remain at least. And of course, I'd like to thank both the organizers of this workshop for the invitation and also the group at Microsoft Research in general for, I'm right in the middle of a 4-week visit. And like Fabio, I'm having a pretty good time here. And well, thanks a lot. So today we're going to be talking about, well, this symmetric exclusion process. So let me start with something simpler, which we all know what it is. Well, when you have a graph like this, an n is always going to be the number of vertices. Let me say this from the outset. You can define random walk on this graph. And today I want to talk about continuous time random walk. What that means is that, well, you have a particle somewhere on your graph. And each edge has its Poisson clock. Maybe the clocks have different rates, but for the time being, you want to think of all rates as being 1. And then when, say, this clock rings, if the particle is on one endpoint, it moves to the other endpoint. Well, if this clock rings, nothing happens because the particle is over here. But then if this one rings, the particle moves again. And, well, it keeps going, right? So this is simple random walk. Well, simple continuous time random walk, that is. And what I'm going to be talking about is a version of this with several particles. They're indistinguishable particles. So this is what I'm going to tell you now is a 3-particle symmetric exclusion process. Well, symmetric means that what I already said about random walk, that its rate of crossing this edge doesn't depend on which endpoint you're at, right? It goes in this direction as often as it goes in this direction. And now the update rule is when an edge rings, you flip the states of its 2 endpoints. So if it rings here, nothing happens. If it rings here, x moves here. If it rings here, nothing happens because there's no particle. And, well, it goes on like this, right? And, well, I'm not going to give the formal definition right now. We'll talk about this later. But I hope the idea is clear. I mean, all of you should be able to write the generator if you so wish at this point. But, right, so what the kind of question you're interested in is, well, as you've all mentioned, it's about mixing times. Well, it's actually part of the title, so it should be obvious. Right, so when you have any Markov chain, in this case we want to talk about continuous time Markov chains, you can define this parameter, the mixing time. Well, assuming the state space is finite and the chain is irreducible, so we know that there's a unique stationary measure and the mixing time is the smallest t for which the transition probabilities from any point in your state space into any subset of the state space, well, they're close to their limiting value, right? Or epsilon close, I should say. Right, so the state space for the random walk is just a vertex set of the graph. The stationary distribution in this case is uniform because of the transition rate to symmetric. For the exclusion process, the state space is subsets of size, well, in this case, size 3 of the vertex set, right? And, well, in general, we're going to be talking about this process here, which I'm going to call exclusion kg, which is a k particle exclusion. And we want to know what the mixing time of this is in terms of the mixing time of one particle. And now the theorem is that it's actually pretty simple to write down. And maybe you just move it over here so that it stays in place as I continue to write. It's this, so well, the mixing time, it's a bit, it says a bit more than what I'm going to state here, but the mixing time of exclusion kg, well, and then you have to choose the epsilon, just choose epsilon equal to a quarter, which is like the standard choice. This is less than a constant, and the constant, by constant I mean something universal, times log of n being the number of vertices, times the mixing time of one random walk. So Rw of g is just a single random walk. So the theorem is telling you this, so that essentially, well, if you compare the ratio, right, of this mixing time to the exclusion, to the mixing time exclusion process, that's at most log n up to a constant factor. And well, I mean, there should be a reason for why that's interesting in some sense, right? So let me, for the time being, I'm not going to say anything about the proof. I'm going to say a few things about the question that motivated this, this work.
So k is fixed here?
No, for any k. So the constant doesn't depend on k. So for any k, well, between 1 and n, well, n with n particles, the process doesn't move, so it doesn't say much.
Is n over 2 or something?
Could be n over 2, yeah. So this is independent of g or nk. It's universal, right? And now, I mean, there's a, at least in my mind, there's one main motivation for this work, which is this. If you look at these x's, at the particles, there's an alternative description of this process, which is as follows. Each one of the x's is doing an independent random walk, following that continuous time rule that I described, except that when this particle tries to jump over here, it's blocked. So you have this exclusion rule that forbids two particles on the same vertex, right? So it's a system of random walks that, but kind of constrained in a certain sense, right? They cannot jump onto each other. And and then you can ask yourself how similar this is to a process of independent random walk. So okay, there are obvious differences, right? For instance, you're never going to have two particles on the same vertex. And on the other hand, there are similar processes, at least from kind of from a high-level perspective, perhaps. So it seems natural to ask if you can say anything in general about the relationship between the two mixing times. It's one way to ask, I mean, whether the way exclusion converges to equilibrium is somehow similar or related to the way the one single random walk converges to equilibrium. So right now what I'm going to do is I'm going to prove the theorem starting from an assumption or a conjecture or whatever that's, well, far from being proven and I think very hard to prove. And this is the conjecture. Well, okay, you could think of this as a heuristic, but I'm willing to bet that something like this is true. And maybe I have to explain what this means. Well, so I'm going to use the symbol here, RWKG, for k independent random walks. So, and well, 1/4 here as well. And maybe you want to put a constant here. So what I'm saying is this, that k particles doing exclusion shouldn't take much more to mix than k particles doing independent random walks. And well, this might seem a bit weird in some sense because, you know, exclusion has obstacles in some sense. One particle blocks the other. But well, because of the symmetry, we have many properties that sort of suggest this is true. And I mean, I'll even give a stronger form of this later. But I mean, at least if you believe me by now, you have this. And this, of course, I mean, this is... Yes?
Maybe you can instead, just worried about the time, maybe you can instead tell us something about the proof of the real theorem without
Sure.
that assumption.
Yes. But let me just say that if you have this, well, since I got started, I'm going to finish this, and then I'll jump to the proof. And I mean, I'm not. So if you have this, then you can prove this, well, with a different constant, perhaps. And this is less than. And this, by a general fact, this is not hard to prove. That I mean, for k random walks to achieve distance 1/4 to equilibrium, you have distance 1/4k for one random walk is enough. And then you can get this inequality. This also comes from general theory of Markov chains. And this is essentially the same result that I have over there, except for having an n here. So in some cases, we know that you can get this with the k. So for instance, for walks on the cyclo or on discrete torus in any dimension, we can get this with the k. I can only get it with an n, right? But it's, that's the way it comes out of the proof. So I mean, in terms of applications, there are many previous bounds about symmetric exclusion. Maybe what I should say is that this matches or improves upon all previous bounds, except in the specific case that I just mentioned, which is when you have a discrete torus and you have k particles, you can get log k instead of log n. But well, following Yuval's request, I'm going to try to move as quickly as possible to the proof. And OK, so there's kind of a very rough outline of the proof is that you first consider mixing for two labeled particles. And what I mean by this is, well, you look at this exclusion process over here, and with two particles, but you give them names. So let's say A and B, right? And you have the same rule. So when you have an edge update, you flip the labels. Right? And then, well, so this is the first step. And well, I'll say something about it. It's not too hard to understand. But then you need to go from 2 to k. Of course, this is not meant to be obvious, right? But and let me just mention that it always suffices to consider k that's less than half of all the vertices, because in the exclusion process, if you look at the complement of the set of particles, right, you get another exclusion process. So if you have k particles, the complement has n minus k. So you can always assume that the number of particles is less than, or at most half of the total.
Do you have a similar result for the interchange process?
Yeah, so, well, for people who know, I mean, I can actually do this part for labeled particles. So that's what's called the interchange process. And I can get this when k over n is less than, well, is bounded away from 1. Right, so anything that's bounded away from 1 I can do with a constant that depends on this ratio here. So that's actually the way the proof works. I wouldn't know how to do it any other way. So I need to consider labels. Yeah. But yeah, for exclusion, suffices to go this far. And right, so, well, how do you do it for two particles? Well, for two particles, it's actually, there's two kinds of couplings that you can consider, and they're sort of complementary, and that's the goal of this part of the proof, to show that, right? So here's coupling number 1. Say you have A and B, and you have A and B like this, right? So it's two different realizations starting from different states. So if you're just trying to couple single random walks, one way you could do it is you let them evolve independently until they meet, and they coalesce from there. Right? So that's how you prove the usual, well, one way to prove the usual Markov chain convergence theorem. Well, it turns out that with this labeled exclusion or interchange process with two particles, you can do exactly the same thing. What you do is, well, you wait until the first pair meets, say A and A, and then you can continue from there until B and B meet. Right? So there's one case of part 1. Let me erase part 2 for the time being, which I call the easy case. And the easy case, so this is coupling number 1, is when for all vertices in your graph, the expected time, well, for the expected meeting time, and I hope what that means is clear, for random walks from VW, right? So meeting time means you let them evolve independently until they find one another. So the easy case is when this expectation is less than, I don't know, 8,000 times t-mix of a single random walk. So I mean, I should say, what's our goal here? Is to say that the mixing time for two labeled particles is at most a constant times the mixing time for one single particle, right? So the easy case is when these expected meeting times like this. In this case, you can use the strategy I just described, and it's going to show that the mixing time, in this case, well, t-mix of, well, interchange process, to use the kind of two labeled particles. And when I write t-mix without an epsilon here, it means epsilon equal quarter. So in this case, you can prove it's something like, yeah, well, maybe, I guess the actual constant, I have 4, and then it's, well, 40,000, certainly enough, since I just want a constant. Now, there's the non-easy case. And the non-easy case, the idea that you have to make rigorous is this. So what does it mean for a graph not to be easy? It means that random walks take a long time to meet. So what does this mean in terms of the interchange process, right? It means that if you start A and B from two states where random walks are unlikely to meet, then the interchange looks like two independent random walks. That's good, right? Because we know how to bind the mixing time at 2 in terms of 1. Now, it's what this is not quite the proof, because here you're asking for all V and W. So when you negate that, you have there exists a pair V and W from which two random walks take a long time to meet. But then what you show is that actually you have the same property for most pairs of initial states. That's the idea. If you have one single pair, what random walks take for a long time to meet, well, you can imagine like this, right? You have this pair here, V, W, and the random walks walk for a long time. They take a long time to meet. Well, if they walk for a time that's like the mixing time, these two places are more or less random. Of course, you can say that the pair is random, but you can say something to that effect, right? Using one of the things you're going to use here is what's called the negative correlation property of symmetric exclusion. Essentially says what's the probability that the two particles are inside a set is at most the product of the probabilities. So if it's non-easy, it's similar, after a burn-in period, it's similar to two independent random walks, and then you're done as well. Right? So this part of the proof is very clean, except for the constant, but it's conceptually very simple. Now let's move on to the hard bit. And the hard bit, I should say, that comes from, well, the ideas come from a paper by Ben Morris, who I already mentioned. It's a paper about symmetric exclusion on discrete tori. Say you take a two-dimensional torus with a large side length, and you want to know what the mixing time of that is. So in order to analyze that, he came up with something that he called the Chameleon Process. And let me try to show you what it is. So, well, so, OK. Let's see. Part 2. From 2 to K. And what you want to do is this. So let's say I want to move from 2 to 3 particles. And I mean, that's not terribly exciting. It could actually use the same ideas for any bounded number of walkers, right? That should be clear. But I mean, so the idea I'm going to use here doesn't move from 2 to 3 to 4. I mean, that will give you a polynomial overhead in K, which is bad. But so now I'm going to show you something that allows you to move straight to any K you wish, right? Any K smaller than n/2. Right, so let's say I want to consider 3 particles, and one of them is going to be red. And actually, let me paint this all red here. And what I want to analyze is not the mixing time of the whole thing, but I want to know how close this is to uniform given the other two particles. It should be clear that it's somehow equivalent, right? I want to know, well, so you have two particles, you have n minus 2 vacant vertices, and how close is this to uniform conditionally on the position of the other two? Right? And so that's the idea. And now you're going to do a series of tricks. So the first one is this. Well, you remember that each edge had its Poisson clock, which we're saying that rings at rate 1. Let's make the clocks ring at rate 2 when clock of edge E rings. You flip a coin to decide whether to use it. And the effect of this is really doing nothing, right? Because we know that if you take a Poisson process with intensity 2 or with rate 2, and you erase half the points as a random fashion, you get a Poisson process with rate 1. So this really doesn't do anything. But what we're going to do is this. So, so you can imagine what happens here, right? So, this edge rings, and you look at the coin to decide whether you're going to move or not. And this edge rings, and you look at the coin to decide whether you're going to move or not. But then, trick number 2 involves what happens when an edge rings that is adjacent to this. So you could look at the coin to determine whether this is going to move here or not. But you're going to force yourself not to look at the coin. And what's the idea here? So if you don't look at the coin, the conditional probability of this being here is equal to conditional probability of this being here. And now what you do is you pretend you had 1 unit of red ink here. And I don't really have pink here. But the right way to do this, according to Morris, would be to paint this pink and this pink. So meaning that these are half red and half white. And now, so this by definition for today is going to be pink. And the trick number 2 is do not look at edges, look at coins of edges that touch some red particle. And for the time being, we only had one red particle. Now it's disappeared. And eventually we get more red particles because we have trick number 3. Which is when, so I should say, we had one red vertex, which was the location of this tag particle. And we have white vertices, which have no ink. And we have pink, which are sort of halfway between, right? So, so the rule now is that when the number of pink is greater than number of white or number of red, I'm going to write it here like all pink flip the same coin. And what I mean by this is that, the pink particles are going to all decide whether they're going to turn red or turn white all together. And they're going to flip the same coin. So here the outcome could be that either these two particles become white, and all red ink disappears from your system, or they both become red. Let me pretend they became red. Just continue this, otherwise it ends. Or it just disappears. And now you have extra moves, so maybe this edge rings, and again this becomes half red and half white. So I have 2 pink now. And I guess I meant here, no, I really need it to be bigger. And then, eventually this particle will move somewhere and will share ink with some other white vertex. And you have something like this. And now they are going to all flip a coin together to decide whether they all turn red or all turn white. And the main point of all this sort of gymnastics here is this, so that the probability that this tagged particle, let me call it red here, is at a vertex x given all the rest. It can be described by the expected amount of ink at site x given all the rest. So you can see that the blue stuff is going to move as it moved before, right? And what I mean by ink is that, well, this is 1 for red. This is half for pink. And this is 0 for white. So that's what I mean by ink. Right? So, and this is just some sort of martingale property. You just need to show that this is preserved at every single step, right? So certainly when they share ink, it means that if a particle had probability P of being here, now it has probability P over 2 of being here, P over 2 of being there. And you have to show that this continues at all times. So, but now comes something else. I mean, this by itself doesn't do much. What does a lot is this thing here. So by the way, this is a chameleon process. And so now let's look at the amount of ink in the system. As at these times, you know that there are times when pink particles completely disappear. They all become white or red, right? So the amount of ink in the system, it doesn't change. You can see that turning one red into two pink doesn't change the total amount of ink, right? And so its evolution happens at these so-called deep inking times, where pink become red or white. And what you have is you start from 1. Well, if you have k particles, you have n minus k plus 1 possible vertices that might be occupied by red. There's also a possibility that you end up at 0. And this evolves randomly. Well, it evolves by taking ever bigger steps, depending on how high you are, right? And I mean, they're unbiased, so they might bring you down as well. So you could die, or you could somehow end up here. So I guess this is drawn on a logarithmic scale, really. But anyway. So I could do both things. And, well, the probability is that, well, let's say the fill is the event that you have n minus k plus 1 red particles. That means that every single vertex that could be occupied by a red particle is going to be occupied. And because of this martingale property, right, at each time step, the amount of ink goes up or down by the same amount, and it's equally likely to do so. The probability of this event, given that you start from 1, is just 1 over n minus k plus 1. And now Morris proved this, that if you're looking at the total variation distance between the law of, of this red particle at time t, given all else, and you want to know how close this is to uniform, well, over the appropriate set, so I don't know, vertices minus whatever is occupied by else, this, well, you have to take an expectation here. You're taking conditional this total variation distance. You have to take an expectation. So what Morris showed is that this thing here is less than 1 minus the total amount of ink in your system divided by n minus k plus 1. You have to take an expectation. And you have to condition on this event that it fills up the whole thing. So I mean, I'm not saying this is obvious. I mean, I'm just throwing lots of things at you right now. But that's the main step in this chameleon process argument. It's just saying that, well, you have this ink. It describes the evolution of the continuous, of the conditional density of this guy. But of course, at some point, you want to get rid of the conditioning, and this is exactly where it happens, except that you have to condition this fill event here. But this is nice because you don't really have to think too much anymore about the conditional distribution of this given the rest. So that's more or less the idea. And I mean, for people who know this evolving set technology that Morris and Yuval developed, this is very similar to the kind of idea they use there, except it's different. Well, it's similar, but it's not the same thing. But right. So, and now let me make a remark here. So, I mean, now your problem is to analyze the evolution of the zinc, random variable condition of this, and well, the way Morris does it is just, well, he knows everything he needs to know about his graph, which is, as I said, it's a discrete torus, right? So you have heat kernel estimates, you have many things that allow you to show, to control the evolution of this. Here we don't have any of this. So what we're going to do is we'll add some quiet periods of length, well, some constant, let's say 10 times the T mix of IP2G. Remember, this is two labeled particles, so this is sort of the same thing as a mixing time. And the thing about these periods is that in these periods where we look at all coins, meaning no color changes. Well, the colors might move around, right? What I mean by this is that you apply the same rule that you have in the usual process. So if this edge ring, the blue particle over here and the pink particle over here, they switch places. So that particles are simply going to move around with no color changes. And of course, that means that we don't apply the strict number 2 here at those times, right? So that's why I say we look at all coins. Right. But and we need this because we essentially don't know what the heat kernel looks like. So right. So what happens here? So I should well, basically, I drew this evolution here. This these are so-called depinking times. And which means that the moments at which the pink all decide to turn red or white. And when you condition this event fill, all you're doing is you're biasing the coin flips by a certain amount that you can explicitly compute towards up. So, right? Because you cannot go down. You cannot go to 0. So you're biasing, you have, well, this is a no-bias random walk, which sort of the size of the steps increases as you go up. And now you're biasing it towards n minus k plus 1. So and what we need to show is essentially, so if you want the total amount of ink to be large, which is what we want here, you want to show that, well, I mean, this is telling you that essentially you're moving very quickly. The discrete time random walk is moving very quickly up in the sense that you can make precise. But what you want to show is that, well, you know, the durations of these periods, they're not constant as I'm drawing here. They're actually random variables. So the time it takes between one depinking and another. And you want to know that, you want to show that those times, they are of the order of the mixing time, essentially. So in a very strong sense. So, and I mean, that's not completely obvious, but the main goal of the remainder of the proof is this. So, it's to show something like I'm going to be a bit technical here, but that if you take any condition, anything on, you look at what happens up to depinking time k minus 1, and you want to know that this thing here, well, divided by some constant T mix of IP2G, which I already said is the order of the ordinary mixing time, and show this less than some constant here. Meaning that it's very likely that this ends in a time of this order. Right? And so, and the way to do it is really you start with any configuration of red and white, and you want to know what happens, right? And I mean, as I said, this really does not depend on this conditioning, as I said, because this condition only affects what happens when they decide to depink. Right, so what do you do here? It's actually not very complicated. So you start with any configuration of black. Well, blue, sorry. So blue are the other particles, right? The ones you're not tracking. The k-1 remaining particles. So it's A and B in this case. So you have a set of blue particles here. You have a set of red particles here. And you have a set of white particles. And I'm going to assume that you have more white than red. And because of what I said, I'm going to assume that they go through a quiet period where no depinking takes place, but which is sufficient because it's of the order of the mixing time of 2 particles. It's sufficient to have the following thing. I mean, essentially, if you look at any 2 particles over here, they're going to be mixed up. So you can pretend they're as likely as any other to be in this state, right? So that's an important thing, that you only need pairwise interactions here. So you have this thing here. And now you want to know what's the probability. So you need a number of depinkings. That's, well, I erased the rule, but you want to know how long you need to wait until the number of pinks becomes larger than the number of white or the number of red. Since I have less red than white here in the beginning, well, the other situation is symmetrical, I need to know how long does it take until the number of red goes down by 1/2, right? So essentially, the main thing, as you can check for yourself, is that you need to bound the amount of time you have to wait. So this is quiet, this is color changing. You need to know how many of these windows you need to see until you see many color changes. And essentially what you do, the basic idea is I want to bound the number of collisions that I have in each one of these epochs here between a white particle and a red particle. Because collisions are good. Collisions lead to things becoming pink. Except that, I mean, if you just count collisions, you're not going to succeed because there might be double collisions, right? Sometimes you're going to have 2 red particles that bump onto the same white thing. And and then you're bound to get into trouble. So maybe this one traveled a lot and came here and bumped onto white, and then it's bad, right? Because then you're counting the same thing twice. So what you need to do is, besides, and I mean, bounding collisions, as long as this is of the order of the mixing time, is really no big deal. Because this white part here, it's a positive fraction, say, more than 25% of graph. More than 25% of edges. So there are lots of particles in here. So proving that there is at least one collision for each one of these is very easy, as long as this is of the order of the mixing time. But for bounding double collisions, you need this extra idea, which comes from these Poisson processes, the clock, the coins, and everything else. So in the end, you end up looking at events like this. So, so you define this notion here for if you take a vertex V here, you call f of V the first collision time, well, the particle, the colored particle, so the red, or first red or white particle that whoever started from V collided with. There might be none, but it's very likely to have some particle. So the bad event, and this you compute for all these guys. The bad event would be something like this. You have red here, and you have, and it moved this way. At this point, it collided with some white. So this means that here you have V, here you have W, which equals f of V. And here you have some V prime that also collided with this one. So this guy is also f of V prime. But how do you control this, right? So, so the basic idea is this. So if you look, so here you had a collision between V prime and W. At this point, you don't look at the coin, and this will become pink in principle, right? Well, maybe there is even an earlier collision, but let's see that this is the first one. But you can pretend that you just evolve the process as usual. You look at the coin, and those two particles flip, and they continue. Right? And then you can ask something like this. Well, OK, given that these particles collided, well, you can say something like this. So given that there's a collision here, this guy is equally likely to have W equal to f of v and to have v prime equal to f of v. Meaning I'm looking at the first collision, right? So when they get here, well, because of the exclusion property and the way I set up the rates and everything, there's a coin, right? So maybe things continue in a way that v hits W. Maybe things continue in a way that v hits v prime. And those two events are equally likely. So using this is somehow saying that, well, the event that two particles meet the same guy is essentially, well, the number of bad collisions of this sort is essentially the number, equal in expectation, to the number of collisions within the red set. So the number of bad events, well, the expected number of bad events, it's less than the expected number of collisions within red. And why is this good? Well, because as we started out, we said we have less red than white. So you have the expected number of collisions with white minus the expected number of collisions with red. This is typically going to be positive. And then you're good to go. So the idea essentially is that once you go through this mixing stage, because these guys are all mixed up here, you can prove that a white particle will probably collide with a red particle will probably collide with a white one, and the probability of double collisions is smaller. And that's it. And that's essentially so you show that with a constant probability, the number of pink grows by a certain constant factor in this phase. And then, well, you repeat it and you're done. So I guess that's it. Thanks a lot.
Any more questions or comments?
So what's the best lower bound? Is just a random walk?
So actually not even that, because, well, if you have the process with labeled particles, then sure, yeah, one random walk gives you a lower bound. If you have a k unlabeled particles, I mean, it's not the case, right? The one random walk is a projection of k exclusion particles. So you essentially have no lower bound, no general lower bound that I know of. And that's kind of the most annoying problem you could think of in some sense regarding all of this. That, I mean, it surely is the case that the exclusion when done over two particles mixes lower than one random walk, but as far as I know, nobody knows how to prove that. Yeah.
And it should be true, say, with log k?
I think it should be true with log k in this generality. Actually, my own feeling is that if you take the process, which I called, what David called, the interchange process with any number of particles, and you put any epsilon here, this should be less than T mix of the corresponding system of k independent random walks. Well, maybe with a constant here, and with the epsilon. And then you get log k automatically. Yeah. But I mean, this is very, very far from being something proven or provable even. I mean, okay, I don't want to push this so far, but it really seems to be beyond our current knowledge of things. And I mean, I think that actually this holds both ways, but you can upper or lower bound these two quantities here.
Okay, let's thank all of today's speakers and Roberto.